Hello everyone and welcome to General Chemistry 2, or Chem 152 that is, lecture number 4 on heating curves and phase diagrams. This covers the final two sections in OpenStack, sections 10.3 and 10.4. Let's begin by analyzing the solid to liquid phase change. We talked about the liquid to vapor phase change a lot in the previous lecture. So this is the process of melting, or what we're going to call fusion, and the reverse process, liquid to a solid, obviously is freezing, but we could describe this as crystallization or solidification. Now, the temperatures at which a substance melts is its melting point, obviously, and as we've learned previously, stronger IMFs generally mean a higher melting point. The normal melting point / normal freezing point occurs at a pressure of 1 atmosphere, just like the normal boiling point does. The energy needed to convert a mole of solid to liquid, or the reverse, is called the molar heat of fusion. So we use the term vaporization for the process of converting a liquid to a vapor or a gas. Now we're going to use the term fusion for converting a mole of something from a solid to a liquid. Molar heat of fusion, or delta HFUS in the subscript. And remember, this also applies to a liquid to a solid. Liquid to a solid. It's the same magnitude of energy change. It would just be, you'd be reversing whether or not you're adding or removing energy from a substance, depending upon which direction the phase change is going. Now, quick side tangent here, not something that you necessarily need to know, but just something I think that's interesting to learn about and see. It's called the phenomenon of supercooling. So if you've heard of supercooling before, this is an interesting process that can occur if you can cool a substance very quickly below its freezing point, and if you do so where you don't allow time for the molecules to become ordered in a crystalline solid phase. So sometimes if you have like a very pure form of a liquid, or it's cooled very quickly, it basically, even though the molecules are moving slow enough, in theory their kinetic energy is low enough to pack into the solid phase, they just don't find the right order. They don't order into that solid phase because either there wasn't like they don't become ordered because they don't have something called a seed crystal. We don't need to get too deep into the weeds with the details here. But what's very interesting is that these fluids are unstable, and they can actually quickly solidify if they're disturbed. So kind of when they're supercooled, they are kind of just moving very slowly. The molecules are still in the liquid phase, but if you shake them or you disturb them, you can kind of knock them into their ordered phase, and when their temperature is low enough, the solid will rapidly form. So here's what supercooling looks like. Oh, sorry for the ad. Alright, here we go. Let's watch this short video on supercooling. Alright, so we've got a bottle of Fiji water. It's cooled down to about, I think it said it was somewhere in the teens. And someone just gives it a knock, they give it a shake, and you can see the solid quickly forming after the liquid was disturbed because the water was at a lower enough temperature to be in the solid phase. Now, it won't always happen so neatly where it'll freeze in the bottle. Sometimes, though, it'll only freeze if it's poured out. And so here's you can see what happens when you pour the water, when you pour supercooled water out of the bottle. All right, and there you can see the ice begins to form. Pretty neat process. Okay, and that's supercooling. Just wanted to show you that real quick. Let's briefly touch on the solid to vapor phase changes. So I described these phase changes in the previous lecture, so you should remember the terms sublimation and deposition. Going from a solid to a gas or a vapor is sublimation, and going from a gas back to a solid is a deposition. At certain pressure and temperature conditions, some solid phase molecules may contain enough energy to move directly to the gas phase. Again, this is sublimation, and the reverse process, where gaseous molecules go directly to the solid phase, is known as deposition. The amount of energy needed to convert a mole of solid to gas, or the reverse, is called the molar heat of sublimation. So delta H SUB in the subscript there. We should also note that due to enthalpy being a state function, you should remember what that term means from General Chemistry 1. The molar heat of sublimation for a substance can be estimated as the sum of its molar heats of fusion and vaporization. So if you sum these two terms together, you get your molar heat of sublimation. And again, this is because enthalpy, delta H, is a state function. Okay, now let's look at phase changes in the context of heating curves. So you probably saw these heating curves in Chemistry at 151 or something similar to this. You probably saw this described in terms of as a phase change diagram, so to speak, or not a phase change diagram, but just analyzing a heating curve for how we can analyze, or how we can view, I should say, the phase of a substance changing as we move our way up this heating curve. So when we start in the bottom left here, we have a solid. So anywhere that's shaded red, we have a solid. And so you can see that as we add energy, as we go left to right on the x-axis, the temperature of the object increases until we hit this point right here. And then notice as we continue to move left to right across the axis, we are still adding more energy. The energy input is increasing, but the temperature is not increasing. And this is because when you are on this flat line right here, melting is occurring. All of the energy you continue to add to the substance goes into pulling these molecules away from one another. When you hit this point, whatever this point is right here, this temperature, you are at the melting point of that substance. So as you continue to add more energy, the added energy is not going to increase the temperature of the molecules, it's going to add more energy to help the molecules separate from one another, and they separate until they are in the liquid phase. Once all of the molecules are in the liquid phase, the continued energy that you add will increase the temperature. So we can see we're on a diagonal where temperature is increasing as the energy input is increasing. Then eventually this temperature increase will again stop once we hit the boiling point for that liquid. After hitting the boiling point, once again our line flattens because the energy we add is not increasing the temperature of those molecules, rather it's helping those liquid molecules separate from one another and they go into the gas phase. So this is our vaporization line. And then finally, once everything has been converted from a liquid to a vapor or a gas, then our temperature will continue to increase as we add more energy. These gas molecules will just move faster and faster. Their temperature increases, and this line could continue off the chart here. Alright, so this is the basic breakdown of how a heating curve works and how we can use it to analyze energy input, temperature, and the phase of a substance. Now we're going to look at how we can break down the math that's actually needed here. So the energy needed to raise or lower the temperature of a substance within a single phase is given by the specific heat of the substance in that phase. So you should remember that term from Chemistry 151, specific heat. That's that little c, the lowercase c here. Now we're going to see that there are three different c's for a substance. It has a different, or a substance will have a different specific heat depending upon the phase that it's in. Whether it's in a solid, a liquid, or a gas phase, it will absorb more or less energy. You should also remember this formula. Q equals mc delta T. So anytime you are doing a calculation where you're on one of these diagonal lines, so these diagonal lines highlighted in red, they require the use of this formula, Q equals mc delta T. How do you know you need to use this formula? Well, remember what I was breaking down on the previous page there? Right, on these diagonals, the temperature is increasing. So temperature is increasing. This is where delta T comes into play. Delta T, change in temperature. Remember, Q is just energy or heat in joules. M is mass, and again, C is that specific heat term. Okay, then our other two places where we need to do calculations are on those flat lines. So during a phase change, either at the melting points or at the boiling point, the temperature stays constant until the phase change is complete. The energy associated with these changes is given by delta H fusion and delta H vaporization, remembering that those stand for molar enthalpy of fusion and molar enthalpy of vaporization. So these two flat lines right here, converting between a solid and a liquid, fusion, converting between a liquid and a vapor, vaporization. All right, let's look at a practice problem. Calculate the amount of energy needed to heat 150 grams of water from a liquid at 25 degrees Celsius to steam at 200 degrees Celsius. So when you are working on these types of problems, I strongly recommend making a little diagram for yourself. So making some room on the page to just hand draw a little diagram. You don't even necessarily need to draw the axes. You can if you want. But I think it's just helpful to draw out the lines of the heating curve to draw the path that you need to follow. So see, you're starting with a liquid at 25 degrees Celsius. So start with a little dot in the bottom left corner here. And then you're going to heat that liquid up until you hit this point right here, which would be the boiling point of water, which would be 100 degrees Celsius. So drawing a diagonal line from 25 degrees Celsius to 100 degrees Celsius. Then our line should flatten out as we undergo this phase change, converting from a liquid to a gas. So drawing a straight line from left to right here where the temperature stays constant. Then once all of the liquid's been converted to gas, we can draw another diagonal line for ourselves as the temperature of the gas increases from 100 degrees Celsius to 200 degrees Celsius. So a diagonal line from 100 to 200 degrees Celsius. We've got some other information here in the problem. We've been given the molar enthalpy of vaporization, the specific heat of liquid water, and the specific heat of water as a gas. All right, so then our approach is what we're going to do is we're going to calculate the energy needed for each step, and then we are going to add them together. We're going to calculate the energy needed to heat up the liquid, calculate the energy needed to convert the liquid to a gas, and then calculate the energy needed to heat up the gas. Let's first start with the energy required to increase the temperature within the liquid. So since we're calculating the temperature on a diagonal line here, we can use the equation Q equals mc delta T. So M is the mass, and this was defined on the previous slide as 150 grams, the mass of the liquid. C, this is the specific heat of liquid water, 4.184 joule per gram degrees Celsius. And finally, delta T, the temperature difference within the liquid phase, so the final temperature minus the initial temperature. So 100 degrees Celsius minus 25 degrees Celsius, which would be about 75 degrees Celsius. So 150 grams times 4.184 joules per gram degrees Celsius times 75 degrees Celsius. If you follow the units, you would notice grams cancel and degrees Celsius cancel, just leaving the unit joules. So we get 47,070 joules. All right, next I'm going to calculate the heat required for the phase change, or the energy needed for the liquid to gas phase change. You can find this by simply taking the molar heat of vaporization given by the number of moles of that substance. So I would take 4.79 kilojoules per mole. This was the given molar heat of vaporization, and I'm going to multiply by simply the number of moles of the substance I'm working with. So I was given 150 grams of water. I'm going to take that 150 grams of water and divide by its molar mass, and that right here, what's in the parentheses, that'll give me moles water, since the grams will cancel and you'll be left with moles, and the moles here will cancel with the moles there, just leaving kilojoules. So we get a value of approximately 339.5 kilojoules. Final step, we need to find the energy required to increase the temperature within the gas. We're on a diagonal line again, so we'll again use the equation Q equals mc delta T. M, mass of the gas, C, specific heat of the gas, 1.99 joules per gram degrees Celsius, and change in temperature of the gas, so that's final minus initial, 200 degrees Celsius minus 100 degrees Celsius, which is approximately 100 times these two values. It gives you 29,850 joules. Our last step then is to simply add these three together. So step 1 gave us 47,070 joules. Step 2 gave us 339.5 kilojoules. I'm going to convert that to joules so it matches the units from step 1 and 2, or excuse me, from steps 1 and 3. And then step 3, we had 29,850 joules. So add these three numbers together. We get 416,420 joules, or we could round this to approximately 416.4 kilojoules. So I would expect your final answer to be somewhere around here, 416.4 kilojoules. Okay, I've got a second practice question for you, but I would like you to try this one on your own. Here, this problem states that benzene, C6H6, melts at 5.5 degrees Celsius and boils at 80.1 degrees Celsius. How much energy needs to be removed from 65 grams of benzene vapor at 92.4 degrees Celsius to convert it into a solid at a temperature of negative 2.3 degrees Celsius? So all of the information you need is given here as well as in the problem here. So see if you can come up with the answer to this problem. Again, try and make a diagram. Start with your vapor at 92.4 degrees Celsius and work your way backwards down to a solid at negative 2.3 degrees Celsius. So I'm going to pause the video and let you give this one an attempt. You might need maybe 10-15 minutes to work this problem through, but give it your best shot. Go back to the work I showed on the previous slides to help you if you need. All right, now I'm going to go ahead and show a little bit of work for this problem. So here's the diagram I came up with. The initial temperature is at 92.4 degrees Celsius. We're going to cool that gas down until we hit the boiling point of benzene at 80.1 degrees Celsius. Then we've got our phase change going from a gas to a liquid. Now we're a liquid at 80.1 degrees Celsius, and we're going to cool that down all the way to the melting point of benzene at 5.5 degrees Celsius. Again, this diagram is not exactly to scale. I just want to show enough room to clearly label all my lines. Your diagram may look a little bit different and more to scale. Now we're at 5.5 degrees Celsius. We're going to remove energy from that liquid. So we've got a flat line, a phase change, the liquid to the solid. Now we're a solid at 5.5 degrees Celsius, and we're going to cool it off a little bit further down to negative 2.3 degrees Celsius. So here's our diagram. Oh, sorry, I thought I went through and showed the steps to outline the answer to this problem, and I forgot to show the steps. My mistake on that one. The correct answer here is 43.8 kilojoules. 43.8 kilojoules. So breaking briefly describe the math on this problem. This curves 1, 3, and 5 would use the formula Q equals MC delta T. So your mass would be 65 grams. Your C value would be one of these C values, depending upon if you are in the gas, liquid, or solid phase. And then the change in temperature would depend upon which phase you are in. I do recommend keeping your delta T values positive because you should in theory be getting positive Q values here given the phrasing of the question. So like for the gas change, I would do 92.4 minus 80.1. That would tell me the temperature change here for the gases. For the liquid, I would go 80.1 to 5.5, and for the solid, 5.5 to 2.3. Those will give you your delta T values. Then for 2 and 4, you need to solve for your number of moles. So you need to take this formula right here and solve for the molar mass of benzene. You should get something around 78 grams per mole. You can use that along with the 65 grams to find moles benzene, and then use those delta H values to calculate the Qs you need for step 2 and 4 here. And again, the final answer is expected to be somewhere around 43.8 kilojoules. Okay, so this is a mid-lecture break. I've got 2 practice problems for you to try. I would again encourage you to pause the video, maybe take 10 to 15 minutes and work on these practice problems. And then here on the next slide are the answers. Okay, let's keep going. Second half of our lecture is on phase diagrams. A phase diagram is a graphical representation of pressure versus temperature data for a substance, and it indicates the different phases of that substance. So we can see pressure is on the y-axis. So as we move up the y-axis, the pressure increases, and temperature is on the x-axis. As we move left to right on the x-axis, temperature increases. And then we've got our 3 key phases labeled: gas, solid, and liquid. Okay, now these lines, so this green line here, this blue line here, and this purple line here, these indicate phase boundaries. These are pressure/temperature combinations where 2 phases coexist in that dynamic equilibrium that we are in a dynamic equilibrium. You again should be familiar with this term. We discussed this when we discussed vapor pressure in the previous lecture. So if you have the precise pressure and temperature condition where you are directly on one of these 3 lines, the green line here between gas and solid, the blue line here between solid and liquid, or the purple line here between gas and liquid. Again, this is a phase boundary, a pressure-temperature combination where these 2 phases would exist in dynamic equilibrium. And if you move across one of these lines, you go through a phase change. So across this purple line, between gas and liquid, across this blue line, converting between a liquid and a solid, across this green line, from a gas to a solid. A few more points to note. Here in the center is the triple point. So the 3 boundary lines meet at the triple point. When you're at the triple point, you actually have a special temperature-pressure combination where all 3 phases exist in equilibrium. Last point to note, up here in the top right corner, is the critical point. The liquid-gas boundary actually ends at what's called the critical point. And if you are above this temperature and pressure, you're in a special phase that's called a supercritical. And I'll explain that further here in a couple minutes. All right, so let's analyze our phase transitions. Let's start with this direction, going across the blue line. If we are going from left to right across the blue line from a solid to a liquid, this is melting. And from right to left across that line from a liquid to a solid would be freezing. Then up here, from, I guess we can say, top to bottom, going in this direction across the purple line from a liquid to a gas, this is vaporization. And in this direction across the purple line, going from a gas to a liquid, this would be condensation. And then the tricky ones to remember, between a solid and a gas, so going in this direction across the green line, from a solid to a gas, sublimation, and this direction right to left across the green line from a gas to a solid, this is deposition. Make sure you understand these phase diagrams. Make sure you know how to label these phase diagrams. You may be asked to label them. So you may be given a blank diagram that just has the lines and the points, and you'll be asked to label where a gas, solid, and a liquid are, what these phase boundaries are, how to label the phase changes, triple point, critical point, things like this. Me personally, the easiest way, or the way that I find this easy to remember, is to think the temperature and pressure, the axes will be labeled. So think about when we go left to right across the axis here, across the x-axis, our temperature is increasing. So if I think about what type of phase is likely to exist out here at really high temperatures and especially at low pressures. If I have high temperatures and low pressures, that makes me think my substance is likely to be a gas. And so I can safely label this portion of the phase diagram gas. Conversely, over here, where we have generally low temperatures, but we have high pressure conditions, this makes me think my substance is likely to be a solid. Low temperature, high pressure, solid. And so I can label this phase of the diagram, or this portion of the phase diagram as a solid, and then liquid is simply in between the two. So remember, high temperature, low pressure, gas, low temperature, high pressure, solid, and liquid is in between, and then you can put the phase changes in from there. Critical points between a liquid and a gas, triple points at the center. Okay, now also explaining that supercritical fluid substance. Oh, let me come back to that in just a second. So here again is that critical point. If you are at temperatures and pressures above the critical point, you are likely to exist as a supercritical fluid. So if you hit that critical point and you just continue to increase the temperature, you are likely to stay as a gas. Or if you hit that critical point and you just increase the pressure, you are likely to stay as a liquid. But if you hit that critical point and increase both temperature and pressure, this purple shaded region that would extend kind of diagonally in this direction, this is where we have a supercritical fluid. So again, critical temperature is the temperature above which a gas cannot be compressed to form a liquid. The critical pressure is the pressure necessary to convert a gas into a liquid at that temperature. When the temperature and pressure both exceed their critical points, the resulting fluid is known as a supercritical fluid. So a supercritical fluid is this interesting phase where it's not really a gas, not really a liquid. It's in between the two. These critical points are directly related to the strength of intermolecular forces. So we can see here as we go from CO2 to NH3 to H2O, our intermolecular force strength is increasing, and the critical temperature and critical pressure are both increasing. Okay, I'll show you a quick video on supercritical fluids in just a moment. One thing I wanted to point out on these diagrams are what are called the normal melting and boiling points. Oftentimes you will see a line on these diagrams, or especially on the y-axis, you will see a line going horizontally across the diagram at 1 atmosphere, or potentially 101.3 kilopascals, and this line represents the normal melting and boiling point line. So where this horizontal line crosses this blue phase boundary, so the phase boundary between the solid and the liquid, this gives us the normal melting point, and so we can draw a line downwards to find that normal melting point. Similarly, where this 1 atmosphere line going horizontally across the figure, where it crosses this purple phase boundary, the phase boundary between a liquid and a gas, this gives us the normal boiling point of that substance. So we can draw a line downwards to the boiling points. Okay, let's watch a brief video on supercritical fluids. And again, apologies about the brief advertisement here. All right, so I'm going to jump forward to the supercritical fluid. Let me find, here we go. This is what I'm looking for. Okay, so you can see, all right, so let me back up and explain what's going on here. Okay, so right now we have a situation where we have gas inside this little container. So this is a sealed container. The gas inside this container is not interacting with the gas outside the container whatsoever. I think it's like argon or xenon, I can't remember. It's one of the noble gases. So this gas, again, is sealed inside a container. This is a very strong, probably a very nicely manufactured glass container, so we can trust the seal on this container. So this container is under very high, the gas inside this container is under very high pressures. So what's going on right now is this gas is pretty hot, and what the presenter is doing is I think they're just spraying the container with some compressed air. So basically they're going to cool the gas down. So you're going to see the gas quickly cools down and turns back into a liquid. So right there we see that rush form, and so now we have liquid in the container, whatever this molecule is. Again, I think it's like argon or xenon, something like that. So we have a liquid in the container. All right, now what he's showing is here's what happens when you heat up a substance that is a liquid. And if you keep this container open to the outside atmosphere, eventually that liquid just boils off. So as you heat the liquid, it forms a gas. The gas boils off because, see, you can see here, the container's been left open and it can escape to the outside atmosphere. Now what he's showing here is whatever substance this is attached to. I'm not quite sure what this is, but this liquid, heat is being transferred to this liquid. Okay, so this liquid is slowly being heated up. Now what we're going to notice here, in comparison what happened in the previous video, in the previous demonstration, is you can kind of see how the liquid kind of just disappears, right? It disappears as gas forms. It just boils off, and again, the liquid quite simply just disappears from the container. What's going to happen here is a little bit differently. As this liquid is heated, you can see it doesn't really disappear, it doesn't really boil off. Rather, the line separating the liquid in the container from the gas in the container kind of just disappears. So watch carefully. Look at that. The line kind of just disappears. So the substance is still in the container. And look, he cools it back down. There's the substance in the container right there. So it's back to a liquid. And then as he heats it, just moving it around, just the motion and the heat transfer from his fingers is enough to heat it back up. And look at that. You can kind of see how the separation between the liquid and the solid kind of just melts away, and it kind of becomes something in between. Sorry, did I say solid? Between a liquid and a gas. The phase boundary kind of just disappears, and it just becomes a substance, becomes a phase that's just kind of in between a liquid and a gas. So supercritical fluids, really interesting, a really, really interesting phase of substances. Okay, it's not going to let me go to my next slide. There we go. Okay, so let's analyze the phase diagram of water. The phase diagram of water reveals a pretty unique property of water. So notice here this solid to liquid phase boundary. On the previous diagrams we were looking at, that phase boundary had a positive slope. For water, however, this solid to liquid phase boundary has a negative slope. One of the major reasons for this is think about how solid water is actually less dense than liquid water, right? Ice floats in liquid water. So as a result, ice can actually be turned to liquid by applying pressure. So this is a very unique property of water, where you can actually change it from a solid to a liquid by applying pressure, because the liquid water is denser than solid water is. Just a unique property of water. So again, if you were, let's say, like right here on the phase diagram, if you increased, so right now we have solid water. If we kept the temperature constant, but we increased pressure, so we moved upwards on the y-axis, eventually you would cross this phase boundary and you would go from a solid to a liquid. You could actually melt, so to speak, the water by applying pressure if you are at the correct temperature conditions. All right, so here's an example type of problem I may give you. Given this blank phase diagram, can you correctly identify and label all of the following? First, you should be able to identify the region corresponding to each phase, solid, liquid, and gas. Then each phase boundary, so solid, liquid, solid vapor, and liquid vapor, or again, solid gas, liquid gas. You should be able to identify the triple point and critical point, as well as the normal boiling point and normal melting points. It may also ask you to draw and label arrows in the correct direction for each phase transition. Last thing to note is to identify the point corresponding to the temperature and pressure below which the liquid phase cannot exist. Okay, so breaking these down, this would be solid, liquid, gas. Phase boundary, we have our solid to liquid phase boundary, our solid to vapor, and our liquid to vapor. We have our triple point here and our critical point here, which is explains this point right here. We have our normal melting point here and our normal boiling point here. And then again, make sure you know the phase transitions and be able to draw and label arrows on these diagrams. Okay, then I've got two practice problems for you at the end of this lecture. First, we've got two phase diagram challenges for you. Here's your first phase diagram challenge. What phase changes will take place when water is subjected to varying pressure at a constant temperature of 0.0005 degrees Celsius, so maybe like right here, 40 degrees Celsius, so maybe somewhere around here, and negative 40 degrees Celsius, let's say maybe somewhere around right here. So see if you can come up with the answer for these three questions. Okay, here are my answers. For the first one, I said gas, solid, liquid. Then second one, gas to liquid. And third one, gas to solid. All right, second phase diagram challenge. Using the phase diagram on the right, determine the state of water at these 6 different phases. And again, the units on these diagrams are a little weird, especially the y-axis. You can see the y-axis scale is actually logarithmic, but just do your best to estimate the state of water or the phase of water at these 6 different temperature and pressure conditions. All right, and here are the answers that I came up with. Yours may be slightly different if you estimated your positioning on the diagram different, but I would expect an answer something like this. Okay, that is the end of this lecture. I hope you found it useful. As always, please feel free to reach out to me if you have questions, and I hope that you have a great day. See you in the next video.